So for this next video, what we're going to talk about is how we can apply Newton's second law in order to derive a system of equations that will allow us to solve for those two unknowns that we had in the previous step. So hopefully everyone has their three vectors acting on that free body diagram decomposed into rectangular form as follows. And hopefully you don't have the first thing you write actually be a little bit of a miswrite like me, but 0 for an x component of the weight minus mg for the y component. Hopefully for the tension provided by cable AD, you got the unknown magnitude, TAD, with a minus on it since it's pointing to the left for the x component and no y component. And again, that just comes from the actual geometry. TAD is going purely in the minus x direction. There's no y direction. And then for the tension in cable AB, hopefully everyone got, well, you definitely got it since you watched me do it, 0.866 TAB and 0.5 TAB. And that's the rounded version. And you might find, like, when I go back, I might actually use the unrounded version since I'm going to be using software to actually make this computation. So what does it mean to be in static equilibrium? Well, static equilibrium just means, if you think about it from Newton's second law point of view, remember that Newton's second law says that the sum of all forces acting on a body, or the resultant force, is equal to the mass times the acceleration. But if something is static, the acceleration is actually 0. So what that means is that the resultant force, which is nothing more than the sum of all forces acting on a body, must be 0. In addition, remember that this is a vector equation. The force is actually a vector. So I'm actually able to take this and write two equations from it. The first equation I can write rather, is that the sum of all the x components of the resultant force acting on a body must be 0, and the sum of all the y components must be 0. And what this actually means is that it's not moving left and right. There's no forces that are tending to push it in the horizontal direction. And what the sum of all forces being y being equal to 0 means that it's not moving up and down. So what are the actual forces acting in the x direction? Well, I have this written in rectangular form now, so I can just take all those three forces and I can write their sum together. 0 for the x component of the weight minus TAD, for the x component of the cable TAD, and then plus 0.866 TAB equals 0. So I'm just going to leave that like that for now, and you'll see why I actually do that. I'm just going to cross off the 0 and show that it doesn't matter. But if you think about, if I were to move the TAD to the other side, which I'm not going to do, what that would tell me is that for this body, TAD pulls to the left, down here, TAD pulls it to the left, and the x component of TAB pulls it to the right. So however much TAD pulls to the left, if this is stationary, the x component of this pull to right must be equal in magnitude. So let's do the actual y component of the vector now. So if I look at the various y components here, notice that the weight has a downward minus mg component. Cable TAD has no y component since it's directed purely in the x direction, and cable TAB has a y component of 0.5 times that unknown magnitude TAB. And all three of those must sum to be equal to 0. And all that this says from an actual physical point of view is that how much the weight of this cylinder actually pulls it down, that must be offset by how much the y component of this tension pulls it up. So the only cable that has the capability to pull in the upward direction is cable AB, because cable AD is purely pulling to the left. So it's going to look a little bit weird for you, but I'm going to actually leave it like this. I'm going to rewrite it like this. 0 TAD plus 0.5 TAB equals mg. So I'm going to actually say that this is equation 2 and this is equation 1. Now what I would like you to actually do, because if you think about what we're looking here, we're trying to convert this system of equations into matrix vector form. So what are the unknowns here? Well, the unknowns are the two magnitudes of those tensions, TAD and TAB. And if you think back to the second lab that you did, or the homework that you did on engineering math and linear algebra, remember that the way you write a system of equations in matrix vector form is you put your two unknowns into a column vector. Then you take, and for the first equation, you write the constant on the right side in your constant vector. For the second equation, you write it there as well. Remember, mg is just a number that we can compute. And then this is our coefficient matrix. We just put all the coefficients of the equations, the first equation in the first row, and the second equation in the second row. So what are the actual coefficients here of the unknowns? Notice that the coefficient here is -1. The coefficient here is 0.866. What I'll challenge you to do is actually fill out the entries in the second row of the coefficient matrix. So you're going to get them from this equation here. Just take the coefficient of TAD and put it there, and take the coefficient of TAB and take the coefficient of TAB and place it in there. So those are the only two entries that you actually need to fill out in order to complete this portion of the lab. But rewrite the whole thing within your answer, please.